Chapter 7.1 Part 3 is about radial electric fields. By the end of this section, you should be able to define radial electric fields. Previously in Chapter 7.1 Part 1, we saw uniform electric fields. So now we have radial electric fields, but I think in Chapter 7.1 Part 1, I showed you what the radial field looks like as well. So we will go into more detail now. Draw and interpret diagrams of electric fields. I showed you some diagrams in Chapter 7.1 Part 1 when we had the introduction to electric fields and uniform electric fields. Describe the relationship between electric field strength and electric potential. So we saw what electric potential is previously, and we also saw what electric field strength is previously in Chapter 7.1 Part 1. So here we will see the relationships. Use equations relating to field strength, that is electric field strength, and potential, electric potential, because we are talking about electric fields, for radial electric fields. Okay, so there earlier we had uniform electric fields, and then we had this equation for uniform electric field, but now we have radial electric field, so we will have more equations for electric field strength. Okay, so here you see a radial electric field. You can see these dark thick arrows which are pointing away from this positive charge are the electric field lines, and these circular dashed lines are the equipotential surfaces. So here what you can observe is the further and further away you move, the greater and greater will be the distance between the adjacent circular equipotential circles or lines. Why? Because when you go further and further away, the distance between these electric field lines increases, which means the electric field strength decreases. So if the electric field lines are closer together, the electric field there is stronger. If they are further apart, the electric field strength there is weaker. Now here it is stronger because the electric distance between adjacent electric field lines is less. So you have more field lines in a certain volume or certain area here. But somewhere here, if you take the same area, you have less field lines. So here the field is weaker, and that's why the distance between equipotentials is increasing the further away you go from the center or away from the charged particle. The radial electric field around a proton or any positively charged sphere. Now there are some important points here. I will tell you what those are. Again, I'll just quickly read this so that again you will understand it better. This anyway, I explained this also, but I'll just read it again. In the region around a positively charged sphere, a point charge such as a proton or a point charge such as a proton. Okay, so here we can say it's a charged sphere or a proton, charged particle that is. The electric field will act outwards in all directions away from the center of the sphere. Why? Because always it will be the electric field lines will be pointing away from the positive charge or positively charged body sphere. As shown in figure A, you will see that the arrows in figure A get further apart as you move further away from the sphere, indicating that the field strength reduces as you move away from the center. This means that the distance between equipotentials also increases as you move further away. I already explained this. The field is the means by which the potential changes. So if it is weaker, the potential changes less quickly. Alright, so here this paragraph is extremely important, this last paragraph here at the bottom. Within a charged sphere, there is no electric field. You can note that down. So if you consider a sphere, inside the sphere, there is no electric field. So how can you shield yourself from an electric field? Is by staying inside something like a metal sphere. For example, now the best place to stay, if you're outside, to stay is when it's lightning is inside a motor vehicle. Okay, so you can remember that with this, because even if the motor vehicle, even if lightning strikes the vehicle, it will go around the vehicle instead of inside. Okay, so you can remember it that way. Within a charged sphere, there is no electric field, as a charged particle would feel no resultant force on it. The overall effect of all the charges on the sphere cancel out within the sphere itself. And so this, you have to remember the first sentence here. So within a charged sphere, there is no electric field. That's the important point. Now, this last sentence here is also very important. Distance measurements for use in calculations should always be considered from the center of a charged sphere. So you don't take it from the surface of the sphere, you take it from the center of the sphere. So distance measurement for use in calculation should always be considered from the center of the charged sphere. You can note those 2 points down. Then radial electric field strength is given by this equation. So again, this is very important. You have to memorize this with understanding. Now we will see what this equation is about. We have seen that a radial field has its field lines spreading further apart simply due to geometry. You can see that. This means that the equation for the field strength of a radial electric field must incorporate this weakening of the field with distance from the charge. The expression for radial field strength at a distance r from a charge q is given by this equation. So this is for radial electric field strength. Now earlier we had the equation E equals V over D, that is for a uniform electric field. Now this is a radial electric field. So what happens is when r, okay, we will see, okay, the expression for radial field strength at a distance r from a charge q is this. So there is a question also to help you understand this better. So q is the charge, r is the distance from a charge. Now remember, over here we learned this, okay, distance measurements for use in calculation should always be considered from the center of a charged sphere. Strictly speaking, this is only correct for a field that is produced in a vacuum, as the value of epsilon naught, okay, by the way, here you have, this is a constant. This is called permittivity of free space. So we have E equals q over, q is the charge, over 4 pi epsilon naught, pi, you know the value pi, and the epsilon naught r square per epsilon naught. This is by the way, this is a Greek letter. That is the permittivity of free space is a constant which relates to the ability of the fabric of the universe to support electric fields. So only thing you have to do is just use this value. Okay, again this will also be given in your data sheet, and you can see 8.85 into 10 to the power minus 12 farad per meter is the value of this. Other substances, for example water, may be better or worse at supporting electric fields. So an extra factor, the relative permittivity epsilon r, would appear in the equation for account for this. Okay, air is considered to be near enough a vacuum that we use the equation given above for electric fields in air. So here, if it is in air, we can assume it's like a vacuum and then use the epsilon naught here. So we can use this equation. That's what they mean. Okay, so let's see how we can use this equation. What is the electric field strength at a distance of 1 angstrom? What is 1 angstrom? That is this much from a proton. So how far? Now remember, this is a very small distance, that's why they use this 1 angstrom. That is actually, they have given you what that is. That is 10 to the power minus 10 meters. So easy. Q is the charge of the proton, that is 1.6 into 10 to the power minus 19 coulombs, which is the same as the magnitude of charge on an electron. Only difference is the sign. Proton positively charged, electron negatively charged. Then 4 pi, you know, you can use the value on your calculator, 3.14 or whatever in the calculator. Then epsilon naught, you can see here, that is that value. R is that. Remember, it's r squared. Then you get this. Volts per meter is the unit. You saw that unit earlier also. One of the units is newtons per coulomb. You can write that, or you can write this, volts per meter. Now here, based on this equation, you can use either one. Okay, you can even cancel out the units and figure it out, but you can write that unit, it's fine. Potential in a radial electric field Okay, so here this is the electric field strength of the radial electric field. Now there was another thing that you are going to learn, that is the potential for a radial electric field. So now we learned the electric field strength for a radial electric field. Now we will see the electric potential for a radial electric field. Electric field strength tells us how quickly the electric potential is changing. A stronger field will have the equipotentials closer together. You can see here it's stronger, they are closer together. The dashed circles are the equipotentials. The equation states that the electric field strength E is equal to the rate of change of potential V with distance x. Now again we saw earlier in chapter 7.1 part 1 E equals V over D. So from that, remember D is the distance. Think of that also. Maybe you can try to remember it that way. By the way, remember what an equipotential line or equipotential surface is. That is a surface or line where the potential will be the same. So for example, if it is 5 volts here, if you go anywhere along this circle, that will be 5 volts. Now here it won't be that value. In this circle it will be a different value. Okay, so here you can see dV over dx minus, this leads to the expression for radial field potential at a distance r from a charge q to be this. Okay, so here you can see you have this, now you have this. Okay, so if you differentiate this, you get that, or simply if you integrate this, those who are taking mathematics and familiar with this, then you get this. Okay, so here you can say when you differentiate, this will be now q 4 pi epsilon naught, that is a constant. Okay, so if you bring the r up, it will be r to the power minus 1. Okay, so this whole thing here is a constant. Think the r is there, r to the power minus 1. Now if you take dv over dx of this, if you differentiate this, now constant you just keep it out, then it will be and there's a minus sign there. Okay, so then minus that comes, then multiplies that, and then you get r to the power minus 2. So when you bring that down, you get r squared, which is this one. Okay, so or else you can simply memorize these two equations if you don't know integration and differentiation. You will see from the equation above that the position of zero potential can be considered to be at infinity. So when r goes to infinity, now q is constant, that is the charge on this, q is constant. When r goes to infinity, v goes to 0. Okay, to help you understand this better, let's see what is the electric potential at a distance of 1 angstrom from a proton. Previously we found the electric field at that same distance. Now we find the electric potential. So again use this equation. Here it's just r, only difference here is r squared. Same way you do it, but here you don't square, just use r. Now here you square, okay, square that value r. Everything else is the same. Then you get 14.4 volts electric potential. Okay, so here you see 1 over 4 pi epsilon naught. We can rewrite that with another constant. We can call it k. Okay, so k is equal to 1 over 4 pi epsilon naught. So here this we can rewrite then as kq over r, right? Then this will be kq over r squared. That's what we have here. See, the constant expression 1 over 4 pi epsilon naught is sometimes written as the single letter k, which is the Coulomb's constant. The value of for k is, see, 1 over 4 pi epsilon naught. Now if you substitute that value for this and do this calculation here, k will be equal to this, then you will have this unit. This means our expression for radial field strength and potential can be written like this. So E equals kq over r squared. Now remember, here it's r squared, here it's r. So you have to remember these two equations, and simple. Now you can remember k is equal to 1 over 4 pi epsilon naught. So very important equations. then you can see here what the fields look like. I showed this earlier when I was explaining chapter 7.1 part 1. So if you have two positive like this, it's like a north pole and a south pole in a magnet. Okay, so you'll have something like this. Then if you have both positive or both negative like this, same magnitude, then you will get this pattern. Only difference is the direction of the arrow. So if it's both positive, the field lines will be going away from the positive. Here if you have both negative, same magnitude of charge, then the field lines will be pointing towards those negative charges. Then here we have a plate which is positively charged and a positively charged point charge. So that can be example an electron or negatively charged field, something like that. Then here, you know, always the field lines go away from the positive charge towards the negative charge. And if it's a plate, you have a uniform electric field. So here, somewhere here, it's uniform. If it's a sphere or a point charge, the field lines will be radial. So you can see it's going from being uniform, parallel here, to being radial there. Okay, and this is say for example a pointed object. Now you may have this on the lightning conductors. Okay, on the top of tall buildings you have these spike like things, the lightning conductors, that is there so that lightning strikes it. It increases the chance that the lightning strikes it instead of anything else around it or that building. Okay, so it is designed like this so that the field at the tip will be very strong. So then as a result the lightning will strike that. I think there was a diagram here also. Let me just check. Okay, sorry, this is the diagram. Okay, so you can see here the field lines are closer together, the field is stronger here, so lightning is more likely to strike that pointed part because the field there is stronger. Okay, so that is actually what you need to know. Now the dashed lines are the equipotential surfaces. I don't think we saw that earlier, but now you can see it. In 7.1 the equipotential surfaces were not shown, but here you can see the equipotential surfaces are shown. So if you go along an equipotential surface, the potential along that particular equipotential surface will be the same. Okay, so let's see. In combining electric fields, by the way, these are important equations. Make sure you study them and you will need them to do the questions here. In a region where there are electric fields caused by more than one charged object, the overall field is the vector sum at each point of all the contributions from each field. So you can see here, that's why I told you here it's parallel because here it's a uniform field. Then here it should be a radial field. So that's why it's going from uniform to being radial there. So that's what we mean by that. If you imagine building the overall field up from the force effects of each contributing field, you can see that at every point you have to work out the resultant force, and in this way you know how a charged particle would be affected there. The sum of all these individual force effects is the overall electric field. Charge is particularly concentrated in regions around spikes. You see more charge here. So the electric field there is stronger. Spikes or points on charged objects. So in the lightning conductor we have spikes like this. This means that they have close field lines and the field will be strong around them. For this reason, lightning conductors are spiked. The concentrated charge will more strongly attract opposite charges, so lightning is more likely to hit the lightning conductor than the building being protected. In fact, the field around a spiked lightning conductor is often strong enough that it can cause charge leakage around the conductor. So imagine like here there's a lot of charge, so there's a lot of charge here, so it just gives out some charge also, then that will charge the air particles around this. So then what happens? The lightning will easily strike that. Leakage through the conductor before charge builds up to a point to produce a lightning strike. The probability of lightning occurring is reduced, therefore protecting the building from these dangers. Okay, so what that means is, now here let's say the AI is charged, so this charge leaks and neutralizes that way also we can say it. Okay, all right, so that is the end of that part, that lesson on radial fields. Make sure you answer all these questions and check the answers in the answer section, answer sheet. The questions here are based on what we learned here in chapter 7.1 part 3 radial field. So briefly, this was the first equation you learned, that is for electric field strength around a radial field. Very important equation. Then if you integrate this, you will get this, or if you differentiate this, you get that. You can think of it like that. Then here you can see this is the difference is just here, it's the same thing, only thing is the r here you have r squared. Then you can see this is 1 over 4 pi epsilon naught, that you can write as a k. See that k is equal to that, and then epsilon naught is a constant, we call that the permittivity of free space, and air and vacuum we can take that value to be approximately the same. But you can see here that is the value. Other substances, for example water, may be better or worse at supporting the electric field, so an extra factor, the relative permittivity, would appear in the equation to account for this. Air is considered to be near enough a vacuum that we use the equation given above for electric fields in air. So this is what we have in for vacuum, but we can use it for air also because of the approximate value for epsilon naught for air, and same as vacuum, approximately equal epsilon naught. Okay, so these two are the two important equations, but remember this is for radial field. Okay, like this, same thing here. But if it's uniform field, you have to use the other equations which we learnt in chapter 7.1 part 1. This is part 3. Then remember this, you can rewrite it as k, then you get this. So the same equation that you see here and that you see there, so 1 over 4 pi epsilon naught, we can write it as k, and if you substitute the value of epsilon naught and pi into this equation, you will get that. So now we can write E equals kq over r squared, V equals kq over r. So here r squared, here r, that's the difference. Then finally we saw this combining electric fields. The dashed lines, blue lines, are the equipotential surfaces. So this is between a positive point charge and a negative point charge, or you can say positively charged sphere and a negatively charged sphere. Then remember this. Okay, so this can be a sphere or a point charge like a proton. And one important thing was, within a charged sphere there is no electric field, as a charged particle would feel no resultant force on it. Then distance measurements for use in calculation should always be considered from the center of a charged sphere. So that's if we use a sphere, but these calculations were involving a proton. So make sure you answer all these questions. I think here you have a sphere, the Van der Graaf generator. And that is the end of that lesson. Okay, if you enjoyed the video, share it with someone who needs it. Leave a comment below the video. Subscribe to the channel if you have not already subscribed, and leave a comment about what was most important or what you found most important in this video lesson. For more information, you can see the video description, where you can access the complete lessons or join our online classes.